Hello, welcome to the course UEC 001. So, in this module, we will discuss in detail how to get the low frequency response of BJT based amplifier, and in fact, in that, let us consider common emitter amplifier using RE model. As we have discussed the RE model in previous module, so on the basis of that, we will consider it. So, if you can recall, three capacitances we have used. Input capacitance was Ci, output capacitance was C0, and emitter bypass capacitance Ce. So by considering the effect of an individual, we will see what is their role and how to calculate the lower cutoff frequency for all. So step by step we will consider. So in the first step, let us see the effect of Ci on the low frequency response. So we will see the effect of input capacitance Ci on the low frequency response. So in general, if you can check, we have discussed FL equals to 1 upon 2 pi RC, which we have derived in previous module. So with the inclusion of this Ci, let me draw the input segment over here. So suppose I'm representing my entire system in a block, and if you can recall, to this we have connected the input capacitance to the transistor Ci and the practical source. So my practical voltage source having a series resistance Rs and a voltage source Vs. And if I'm saying that this Vi is effective input voltage which appears across the system, and the value of resistance which we have measured across the system is Ri, then you can check, uh, these two resistances seems to be connected in series configuration. Therefore, the value of FL, and I am using a notation I because we are dealing with the input side capacitor, will be equals to 1 upon 2 pi. Now, rather than R, we will have Rs plus Ri, where Rs is my source resistance and Ri is overall input resistance of the system multiplied by Ci, and we will have this lower cutoff frequency when we are considering that in entire system only this capacitance, input capacitance, have been considered. Okay, so meaning over here is, we are assuming that the remaining two capacitances, that is my output capacitance and emitter bypass capacitance, seems to be of the short circuit, and the only capacitance to the input side is only the Ci. Okay, so at this particular frequency, lower input frequency FLI, the input effective voltage Vi will be 70.7% to its maximum value when we consider that this input capacitance Ci is the only capacitive element participating to the input side of the amplifier. Okay, by considering this situation, we can prepare now a localized input network, a practical voltage source, input capacitance. Now, considering the same amplifier circuit, we have taken voltage divider bias common emitter amplifier circuit. So these two were R1 parallel R2, and that is my Zi, which we have calculated in the previous module, which will be equivalent to beta times Re. and this is my input capacitance Ci. So across the input side of my overall system, if I'm saying that this segment is contributing the system, so this is my Ri, and you can check Ri is nothing but R1 parallel R2 parallel Zi. Okay, so it is having an effective voltage Vi over here, and let me write the name of the circuit. This is my localized AC equivalent circuit for input capacitance Ci. So this is my localized AC equivalent circuit for input capacitance Ci. And now I can easily calculate the effective voltage Vi with reference to the source voltage by using voltage division rule, by using voltage division rule, and it is my Vi will be equals to now Ri, that is my overall input resistance of this system, multiplied by supply voltage Vs, divided by addition of all. So it is Rs plus Ri plus reactance of this resistance. So I'm representing minus JXCI. So this is my overall input voltage, or I'm saying that this is my effective voltage appears across the input side to the amplifier. And at this particular site, the lower cutoff frequency FL, notation I is indicating the inclusion of input capacitance. It will be termed as 1 upon 2 pi Rs plus input resistance of the system multiplied by input capacitance Ci. So this is my first lower cutoff frequency with the inclusion of input capacitance Ci. Now the second segment, first segment we have discussed the effect of Ci. Now let's see what is the role of C naught over here. Okay, so let's see the effect of output capacitance or coupling capacitance C naught on the low frequency response. So let's check the effect of coupling capacitance C naught to the low frequency response. And for understanding, let me draw that this is my system, overall system, and suppose my system having an output resistance R naught. So we will take the output by coupling an output capacitance C naught to the external load resistance RL, across which we are interested to measure the output voltage V naught. So with this RC combination, again I am saying that my lower cutoff frequency, and now I am defining O. So notation O is representing the inclusion of this my coupling capacitance C naught, which we have coupled to the output side, and it will have a series resistance of R naught and RL. So my R will be replaced by 1 upon 2 pi R naught plus RL times C naught. So let's see the role of this coupling capacitance over here. So at this particular lower frequency, it means that my output voltage will be having a value of 70.7% if I am considering that there is a contribution of this capacitive element only. That means over here I am considering that my input capacitance Ci and my emitter bypass capacitance Ce, these will behave like short circuit. If these two behaves like short circuit, that means the only participating capacitance is my output coupling capacitance C naught, then I will have the output voltage at this lower frequency 70.7% to its maximum value. Okay, and under this situation, let me draw the localized AC equivalent circuit for common emitter configuration, and the circuit will be output resistance of my amplifier in parallel the collector resistance RC, and we have connected a coupling capacitor C naught to the load resistance where we are measuring the output voltage V naught, and we have measured R naught across here. This is the overall output resistance which we have measured from the output characteristics. So this R naught was measured from output characteristics of the common emitter configuration. So because we are talking about the common emitter configuration, and this is my localized AC equivalent circuit for C naught. So first you can check the value of this R naught equals to my resistance small r naught, that is the slope which we have measured from the output characteristics of the common emitter configuration, parallel with the collector resistance Rc. Generally, for RE model which we have used, typical value of this R naught is infinity ohm. So if you are taking the parallel configuration of both, then the general term of R naught, which is the output resistance of my system. So over here, this particular segment is representing my system, and this will be equivalent to RC. Second condition for this system is required. We have to we have to replace the source voltage by 0 volts. That means we have to replace this by a short circuit. For the analysis of output side, we have to apply this condition. Okay, so that is my localized circuit, and in this situation the value of lower cutoff frequency FL naught will be equals to 1 upon 2 pi R naught plus RL times C naught. So this is the cutoff frequency at which we will have the output gain from its maximal value to 70.7%. Now let's see the final one, the effect of CE, effect of emitter bypass capacitance CE on the low frequency response. So we have earlier we have divided our discussion into the three sections because three capacitive elements we have used, Ci, C naught and Ce. We have seen what are their roles. Now let's see the impact of the Ce. And if my system to the emitter side is representing this, and I am looking from the measurement of effective emitter resistance Re, whose bypass capacitor is connected Ce, then I want to check my effective lower cutoff frequency. I am representing notation E. This is representing the use of emitter bypass capacitance Ce over there. So it will termed as a frequency 1 upon 2 pi Re, the resistance measured at the output of the system multiplied by Ce. Now over here, the only part is what is the value of this Re. So for that, consider the situation that my Ci and C naught in this situation equivalent to short circuit, so that the contribution of this Ce only can be studied. So in that situation, the localized equivalent network will be like this. So this is my emitter resistance Re. Across here, I will measure resistance Re. This is my emitter bypass capacitance Ce, and this is the resistance for the transistor, and it is calculated as R dash upon beta plus Re, where the value of this R dash is the parallel combination of Rs with R1 and R2. Rs dash is parallel combination of this. Beta is there. Re we have earlier solved. Re is my Vt, that is thermal voltage, divided by DC current flowing through the emitter terminal, IE. Okay. So now maximum gain can be achieved, and in fact this is my Rs dash. So I have to calculate the value of small Re, and now you can check small Re will be equals to Rs dash parallel with emitter resistance Re. So that is my Re. So you can put this value Re over here, and the voltage gain can be calculated as simply output voltage upon input voltage in this situation, and it will turn as minus Rc upon Re plus emitter resistance Re. Now depending upon the frequency, the maximal value of this gain can be achieved when Re emitter resistance is equal to 0. Means emitter resistance will be 0 if emitter bypass capacitor Ce is replaced by a short circuit, and it will replaced by a short circuit at high frequency. AV max can be achieved, which will be equal to minus Rc upon Re when Re will be equal to 0 ohms. And practically it is possible for a higher frequency values where capacitor will be replaced by a short circuit. So entire current will flow through the emitter bypass capacitor. Or one can neglect the value of this resistance, then it would be happen. At FLE 70.7% value of this AV max could be achieved. So that is the contribution of this capacitance Ce. Okay, so idea will be clear if we see one example. So let us solve. Determine various lower cutoff frequencies if details are given as VCC equals to 20 volts. Different values of resistances have been given as Rs equals to 1 kilo ohm, R1 equals to 40 kilo ohm, R2 equals to 10 kilo ohm, C equals to 4 kilo ohm, E equals to 2 kilo ohm, and a load resistance RL equals to 2.2 kilo ohm. Various capacitances have been given as the value of Ci is given as 10 microfarad, C out is given as 1 microfarad, and emitter bypass capacitance C is given as 20 microfarad. Beta of the transistor is given as 100. R naught is given as infinity. So these are the values given. We have to determine the value of FLI, FL naught, and FLE. What will be the value of these terms? Okay. So for better understanding, let me draw the circuit diagram. So this is the database given. So for the solution purpose, you can check we have to apply RE model, and in that RE model, the value of RE is VT divided by DC current IE, and for DC current we need the DC equivalent circuit for this. Okay, so we are not going into too much detail. Let's see, are we in a position to apply approximate analysis? So let us check the condition of approximation. Condition of approximation, and it was beta times Re should be greater than or equals to 10 times of R2. So 100 multiplied by 2k should be greater than or equals to 10 multiplied by 10k, and we can see that 200k is greater than 100k, so condition is valid. That means we can use the approximate analysis. And what my approximate analysis says that my DC current IB will be equals to 0. Okay, and the two series currents, these currents I1 and these currents I2, these two will be equal. And I am interested to find the voltage, base voltage of this VB. This can be calculated from voltage division rule. VB equals to 20 overall voltage multiplied by the resistance across which we want to find. So it is across resistance R2, that means 10 divided by 40 plus 10. Kilo will be cancelled from numerator to denominator, therefore I have divided, and this will come up a value of 4 volts. So my base voltage VB equals to 4 volts that we have calculated from the DC part, DC analysis. Now, assuming that my transistor is made up from silicon, that means the typical value of VB equals to 0.7 volt. Now, I can easily calculate the emitter voltage VE, which is my VB minus VBE, ultimately 4 minus zero point 0.7, that is 3.3 volts. Further, we also know that V equals to RE into emitter current IE. Therefore, I can calculate the DC emitter current equals to emitter voltage upon emitter resistance RE. And this is my 3.3 divided by 2 into 10 raised to power 3. So my DC current is 1.65 milliampere. And once this value is calculated, so I'm assuming that we are working at room temperature, and if we are working at room temperature, that means the thermal voltage VT equals to 26 millivolt. Hence, my emitter resistance RE is 26 into 10 raised to power minus 3 divided by value of IE 1.65 into 10 raised to power minus 3. That is the value of RE, 15.76 ohm. So we have calculated the value of RE. And if you can recall the terms, because now we require certain parameters for small signal analysis. My Zi was beta times of Re, so it will be 100 multiplied by 15.76, or it is 1.576 kilo ohm. My Z naught will be equals to R naught infinity ohm, and over here my gain, that is AV. So over here my voltage gain will be nothing but so for this I want to draw here the AC equivalent model. Before this I want to draw its AC equivalent model, and AC equivalent model using RE. So this is my AC equivalent model of common emitter amplifier using RE. This is my source resistance Vs, R1 parallel R2. This is my Zi, beta times of input current IB, which is flowing across here, input current IB. And this is my RC. RE is replaced by a short circuit, and this is my load resistance RL. Okay, so this is and current flowing through here is my current IC. So now you can check across this parallel, across this output, I am having a resistance RL dash, which is nothing but RC parallel RL. Therefore, my voltage gain will be minus, it is RL dash divided by RE. So it should be RC minus times RC parallel RL divided by RE. Okay, so this will come as minus 4K parallel. Value of RC is 4K and it is 2.2K divided by 15.76, which is my approximately 90. So this is the value of voltage gain AV for the given problem. Now let us check the overall voltage gain AVS. Let us calculate my overall voltage gain AVS RI, whose value is R1 parallel R2 parallel ZI. In fact, I will calculate this RI over here. So value of, and across this I am having the input voltage. So I can calculate this input voltage from voltage division rule, and this is Ri multiplied by source voltage Vs divided by Rs plus Ri, or the ratio of Vi upon Vs will be equals to Ri upon Rs plus Ri. 40K, 10K, 1.76K, and they all are connected in parallel configuration, and their parallel equivalent is 1.32 kilo ohm. That is the value of R. So one can easily calculate 1.32 divided by 1 plus 1.32. Kilo will be cancelled out from numerator and denominator, and this quantity becomes 0.569. Therefore, my overall voltage AVS will be equals to overall output voltage upon overall input. So it can be categorized V0 upon Vi into Vi upon Vs. This quantity V0 upon Vi, we have calculated the midterm voltage gain AV, and it is minus 90 multiplied by 0.569. So my overall voltage gain AVS inclusion of source voltage will be equals to minus 51.21. Now let us calculate the all frequency terms. So let's begin with FLI to the input side, 1 upon 2 pi, it is my RS plus RI times CI. So directly putting the value 1 upon 2 into 3.14 multiplied by Rs is 1K into Ri we have calculated, and this value 1.32 multiplied by 10 raised to power 3 as given in kilo ohm, and the value of input capacitance Ci was 10 microfarad, so 10 into 10 raised to power minus 6, and this frequencies comes up an approximate value of 6.86 hertz. So this is the lower cutoff frequency with the effect of input capacitance Ci. Now let us determine the value of FLO with the contribution of output capacitance. So 2 pi R naught, and now R naught will be my RC plus load resistance RL times C naught. So 1 upon 2 into 3.144 plus 2.2 into 10 raised to power 3 multiplied by the output capacitance, and output capacitance was given as 1 microfarad, so 1 into 10 raised to power minus 6, and its value is approximately 25.68 hertz. Now let me calculate the last component FLE, and this is 1 upon 2 pi RE times CE. So before that I have to calculate the value of RE, which is my RS dash upon beta plus RE in parallel with resistance RE. So let me calculate RS dash first, which is RS parallel R1 parallel R2. So this quantity becomes 1 kilo ohm parallel 40 kilo ohm parallel 10 kilo ohm, and this quantity is equivalent to 0.889 kilo ohm. Therefore the quantity Rs dash divided by beta plus Re will be equals to 889 divided by 100, and we have calculated the value of Re is 15.76. So this quantity becomes 24.65 ohm. And let me calculate now this value. This is 24.65 parallel with Re, and value of Re is given as 2 kilo ohm. And this parallel combination is 24.35 ohm. Therefore, my FLE, I can write the value of FLE by putting 1 upon 2 into 3.14 multiplied by 24.35 multiplied by 20 microfarad, 20 into 10 is to the power minus 6, and this quantity becomes 327 hertz. So if one has to plot the curve, and suppose I am saying that with reference to the maximal level, we will have the frequencies like this. If suppose this is my maximal gain, then the value of, let me rewrite their values, FLI, FLO and FLE. So FLI we have calculated 6.86 hertz, FLO 25.68 hertz, and FLE 327 hertz. So I will have this curve. If this was the maximal level of AB, and this is the level of 0.707 of AB. So this is indicating my FLI, the lowest frequency. Then I will have somewhere this frequency over here, FLO and FLE with their values. So this is the frequency response of the given problem. Okay, so we are stopping the discussion over here. Thank you.